Hey everyone, and welcome back for another deep dive. Today, we are cranking up the heat, exploring the hottest things in the universe. And to help us with this, we'll be taking inspiration from Vsauce's video about, well, yeah, the hottest things in the universe. But before we get into all that, I want you to just take a second and think, what's the absolute hottest thing you can imagine?
It's funny you should say that because what we think of as hot here on Earth, well, it's really just a tiny sliver of the temperatures that exist out there in the universe.
Yeah, it's incredible, isn't it? I mean, we're talking about temperatures that are almost impossible to comprehend. But I guess a good place to start is with something we all know, our own body temperature, 98.6 degrees Fahrenheit. That's the magic number, right?
Well, not exactly. It's not really a static number, you see.
Huh.
Our bodies are constantly generating heat, kind of like little internal combustion engines. So your temperature actually fluctuates throughout the day.
Really? I had no idea. So when am I the hottest?
You're actually at your coolest in the early morning, around 4:30 a.m., believe it or not.
Wow, that's when I always feel the coldest. But I guess that makes sense if my body's just starting to warm up. So then when am I the warmest?
Your warmest point is usually in the evening, around 7 p.m. It's only about a 1 degree difference, but it shows how dynamic our bodies are.
I have noticed that I always feel the most energetic in the evenings, so maybe that has something to do with it. But it's amazing how our bodies maintain that balance even when we're exposed to different temperatures outside.
Absolutely. That balance is crucial. Even a small shift can have big consequences, like with a fever. Hitting 108 degrees Fahrenheit, that's incredibly dangerous, often fatal.
That is scary. Okay, so that's our human baseline, 98.6, give or take a degree. But what about the hottest things on Earth? I'm thinking like scorching deserts, erupting volcanoes.
Well, you're on the right track. Death Valley, in California. That holds the record for the highest air temperature ever recorded, a scorching 129 degrees Fahrenheit.
Wow, that's hot enough to fry an egg on the sidewalk, literally. It's amazing how anything can survive in that kind of heat.
It is. But even Death Valley pales in comparison to, say, molten lava.
Oh yeah, lava. Now we're talking. What kind of temperatures are we looking at there?
Lava erupting from a volcano is around 2,000 degrees Fahrenheit.
That's just insane. I remember that Vsauce example where he used a Fresnel lens to melt rocks. It's incredible how powerful concentrated sunlight can be, even from 93 million miles away.
It is. And that leads us perfectly to the ultimate source of heat in our solar system, the sun.
The sun, now that's a whole other level of hot.
It is. Its surface temperature is a scorching 10,000 degrees Fahrenheit.
10,000 degrees, wow. But isn't the core even hotter?
Much hotter. The sun's core, where nuclear fusion is happening, reaches a mind-blowing 28 million degrees Fahrenheit. To even start to grasp that kind of heat, we need to switch to a different temperature scale, called Kelvin.
Kelvin. Okay, so when we're talking about these extreme temperatures, it sounds like we need a whole different way of measuring heat. Can you explain a bit more about what makes the Kelvin scale so special?
Sure, Kelvin is different because it starts at absolute zero.
Absolute zero. What's that?
Absolute zero is the point where all molecular motion stops. It's like the ultimate cold. It's 0 Kelvin. And that means that 0 Kelvin represents the complete absence of heat. This is super important when we're dealing with temperatures as high as the sun's core.
Okay, so 0 Kelvin is as cold as it gets, and then the sun's core is millions of degrees on that scale. That's a massive temperature range. But what does that kind of heat actually do? Can you give me a sense of just how much energy is involved?
Sure. Imagine this. If you could somehow heat just the head of a pin to the temperature of the sun's core, it would be lethal to anyone within 1,000 miles.
Whoa, that's incredible. It's hard to even wrap my head around that kind of power. And all that energy is constantly radiating out from the sun, reaching us as light and heat. And speaking of light, it always seems like heat and light are connected somehow. Like the hotter something gets, the brighter it glows.
You're absolutely right. Everything in the universe that has a temperature above absolute zero emits electromagnetic radiation.
Mm.
Even us. We give off infrared light, although we can't see it with our naked eyes.
Right, like
Yeah.
in that Vsauce video where they showed a guy wrapped in a black trash bag. You couldn't see him normally, but with an infrared camera, he was glowing.
Exactly. And as something heats up, the wavelengths of radiation it emits, they get shorter and shorter, and it shifts from infrared to visible light. So it starts to glow red, then it goes through the whole rainbow of colors as it gets hotter and hotter, eventually moving into ultraviolet light, X-rays, and even gamma rays. That's what's happening with the sun. The incredible heat generates light across the entire electromagnetic spectrum.
Wow, so we go from invisible infrared to the blinding light of the sun just by increasing temperature. That's mind-blowing. But it also makes me wonder what happens to matter itself at those extreme temperatures. Like, does it change form?
Well, that's where we get into something called plasma. Plasma is the fourth state of matter.
Yeah.
You've got solids, liquids, gases, and then plasma.
Okay, I remember learning about plasma in school, but I always thought of it as something kind of exotic, like something out of Star Trek.
Well, it's not as sci-fi as you might think. Plasma is what happens when atoms are stripped of some of their electrons, and it creates a sort of electrically charged soup of particles. And guess what? The sun, it's made of plasma.
Really? The sun is a giant ball of plasma. That's wild. So plasma is basically superheated, energized matter. And it's not just in stars, right? I mean, Vsauce mentioned something about creating plasma in a microwave.
He did, but please don't try that at home. It's very dangerous.
Definitely not trying that at home. Okay, so we've got plasma, the fourth state of matter, and we've got the incredible heat of the sun. But is that the hottest thing out there? Or are there even more extreme temperatures lurking in the universe?
You know, we were just talking about the sun and stars being made of plasma. Well, at 1 terakelvin, even the particles inside atoms start to melt down.
Meltdown. What does that even mean on that kind of scale?
It means the protons and neutrons in the nucleus, you know, those particles we normally think of as being like super solid, super fundamental, they break apart. They basically turn into a soup of quarks and gluons.
Okay, so we go from atoms to plasma, and now even the parts of atoms are getting all soupy. That's some serious heat.
It is. And believe it or not, we can actually reach those kinds of temperatures here on Earth.
Wait, really? Where? Like in someone's backyard with a super-powered Fresnel lens?
Not quite. Scientists at the Large Hadron Collider in Switzerland are smashing protons together at incredible speeds, and when they collide, they generate temperatures in the terakelvin range. And sometimes they even exceed it into petakelvin and exakelvin ranges.
Petakelvin, exakelvin. Those sound even more intense than terakelvin. What kind of scale are we even talking about here?
To give you an idea, 1 exakelvin is a billion Kelvin. It's 1 with 18 zeros after it.
Whoa. That's hard to even imagine. I mean, those kinds of temperatures only existed for like fractions of a second after the Big Bang, right?
You got it.
So it's like they're creating tiny little Big Bangs in Switzerland. That's both amazing and kind of terrifying. Are we sure these little Big Bangs are safe?
Don't worry, those extreme temperatures, they only last for incredibly short periods of time. We're talking fractions of a second. And they're confined to a tiny space.
Yeah.
It's not like Switzerland's going to turn into a giant quark gluon soup.
Okay, that's good to know. But still, if we can create those kinds of temperatures here on Earth, it makes you wonder, is there a limit? Like, what's the absolute hottest possible temperature? Is there such a thing?
Well, that's where we bump up against the limits of our current understanding of physics. You know how we were talking about how as temperatures increase, the wavelength of radiation gets shorter?
Yeah.
Well, there's a point where that wavelength becomes so small that it reaches the Planck length, the smallest possible distance in the universe.
So like a physical limit, like we literally can't go any smaller than that.
That's what physicists currently think. And the temperature at which that happens is called the Planck temperature. It's a mind-boggling 1.41 by a 0.32 Kelvin.
Okay, I officially can't even process numbers that big, but what does it even mean? What happens at the Planck temperature? Does everything just like melt into nothingness?
That's the big mystery. See, beyond the Planck temperature, our current laws of physics break down. We don't really have the tools to describe what would happen. Some theories suggest that at those kinds of crazy energies, a black hole could spontaneously form from pure energy. It's called a Kugelblitz.
A Kugelblitz. Okay, now there's a term I've never heard before. It's pretty wild to think that something that extreme could theoretically exist. Like, it really pushes the boundaries of what we thought was possible.
It is. And even though we can't actually reach the Planck temperature in any practical way, just knowing that it exists as a concept really challenges our understanding of heat and energy and even the fabric of reality itself.
I think my brain is officially fried. So we've gone from our own body temperature to temperatures that could, like, create black holes. It's been an incredible journey. But before we totally lose it, maybe we should bring things back down to Earth for a minute.
You're right. Sometimes it's good to get a little perspective. That's where the comparison between, say, a human and the sun's energy output is really interesting.
Oh, yeah. Vsauce talked about that. It's a pretty strange comparison, isn't it?
It is. See, even though the sun is way hotter than us and puts out an insane amount of energy overall, if you actually compare the energy output per cubic centimeter, A human generates more energy than the sun.
Wait, seriously, how is that even possible? I mean, the sun is this gigantic nuclear fusion reactor. How can we even come close to competing with that?
It all comes down to size and density. The sun is so massive that its energy is spread out over this huge volume. So even though each cubic centimeter of the sun is super hot, it's not as densely packed with energy as, say, a cubic centimeter of a busy human body.
That is mind-blowing. So even though the sun is this giant, powerful star, in a way, we're actually more energy dense. It's like saying a tiny little sparkler can be more intense than a giant bonfire if you're close enough to it.
Exactly. And it really drives home the point that sometimes even the most familiar things can be incredibly powerful and
Mhm.
complex. We just need the right perspective to see it.
So we've gone from our own bodies, which are pretty amazing in their own right, to the sun, and then all the way to the Planck temperature, this like ultimate limit of heat. This really makes you realize just how much is out there, you know?
It is pretty incredible, isn't it? And the thing is, even with all our scientific advances, we're still just scratching the surface when it comes to understanding temperature, especially at those extreme ends of the spectrum.
I mean, just think about the Planck temperature for a second. What could even exist beyond that point where everything we know about physics just kind of falls apart? It's mind-boggling.
Absolutely. And it's those kinds of questions that really push us to keep exploring, to keep searching for answers. It's what makes science so fascinating.
Yeah, you're right. Like if we can create temperatures hotter than the sun right here on Earth,
hmm
who knows what we'll discover in the future? There's a whole universe of possibilities out there.
I completely agree. I can't wait to see what the future holds.
Well, on that note, I think it's time for us to cool down a bit. After all that talk about extreme heat. I don't know about you, but I'm suddenly craving a big glass of ice water.
Sounds good to me.
Thanks for joining us for this deep dive into the hottest things in the universe. It's been an incredible journey, and to all of you listening, we hope you've enjoyed it. And remember, keep asking questions, keep exploring, and never stop learning. Until next time.